This is the ninth of the videos in the series on the theory of everything, which is just talking about some of the considerations, not a description of a full theory. I want to perform some calculations today using the equations that were given in the last two videos. The equation that conserves energy states that the total separation between two bodies represents the total energy. This is the R, the total separation between two bodies, and that is equal to the separation between the bodies in space, of which I'm going to allow 3 dimensions, or up to 3 dimensions. The sum of those is the sum of the squares of the separation in space, and gives you the total separation in space. And this represents the potential energy in a non-linear manner. This represents the total energy. And plus the velocity of the which is the change in the distance between the two bodies with time at any instant, times the period of the system squared, and I called this the x dimension, and that represents the kinetic energy, and you can also correct for time dilation, which I'll just put down here that it's additional energy, and it's related to the speed of light times a particular time interval that represents the difference between the times of the two bodies in the time dimension of the system. So this is also kinetic energy, and it's the relativistic increase, which we can talk about as an increase in mass. And talking about mass, of course, this is per unit of mass, or rather per unit of masses, in the sense that you multiply each of these by the product of the masses of the two bodies, which gives you the multiplication due to the fact the bodies that have more than one unit of mass. So you multiply the mass of the Earth and the Moon, and you multiply each of these units with that. But since I'm going to be talking about the velocities and periods and so on, these are not affected by the mass as far as we're concerned with these calculations. Now, I called this the x dimension, which is the invisible dimension that represents a separation between the bodies that's associated with the velocity between them. Now, the solutions to these, there's also an equation to give you the conservation of momentum, which is that the total velocity squared is equal to the sum of the velocity in each of the dimensions of space, or of any of the dimensions, the velocity of space or in the x dimension, any velocity at all. And this is constant, meaning that if you include, and remember I had a circle, and I said that all orbits are circular on the surface of this spherical sphere that surrounds the central body, and the orbiting body circle on the surface of that sphere, which maintains the constant energy that we referred to before, and this velocity gives you the constant momentum. Now, if the body is in a circular orbit, then it is in a orbit like that on the surface. This is the energy shell here, and this is the orbit of the body going around, and if this were the moon, then these are two dimensions of space. This R1 and R2. If you turn the sphere around 90 degrees, you can get one dimension of space and one dimension of the X dimension, which is the one with the represents the kinetic energy. And if this circle is then here, the moon is going around in a circle separated from the Earth by this X dimension separation, which represents the velocity. So, and that's constant, so that it stays at that distance in the X dimension, but it's orbiting in the two Y dimensions. So we've got two dimensions of space here and one of the X dimension. Now the equation, the solution for the equations to describe that movement is as follows: that the distance in any one of the space dimensions is equal to the maximum dimension, which is r, times the cosine of the period this is time w times time. W is the represents the frequency, and this is equal to 1 over the period. And this is there's no 2 pi in here, as you sometimes will see. If you have 2 pi in here, then that means that your frequency is in cycles. Your period represents the time for a complete cycle. I use the time for a radian, which is the more natural measurement of frequency, so I don't need the 2 pi. So that's what the that's what the one of the space coordinates changes, and the other one is a sine. And the value of the distance is equal to the I use capital letters more. It's easier than drawing an R, a small r. The radius is equal to the velocity times the time, and as is kind of obvious, the distance is equal to speed times time, and this is the time for the body to travel one distance of a radius around the circumference, which is a radian of angles. So there's a circular orbit. The equation then as a whole is like this. If you have that r naught squared equals rn squared plus v squared t squared, that's the equation that you had. And when you have a circular orbit, then these two are equal, and the radius is equal to the total separation divided by the square root of 2, because this is equal to this, that is equal to that, this is equal to half that, and since they're squared, we have to find the square root to get the relationship. So that's the solution to the equation for a circular orbit. And if you have, however, a body that is going straight up and down, such as this. It's not going any very far. It's traveling only like from, if this were the Earth, if this were the Earth, it's not meant to be. If it's, I'll draw the Earth in the center here. This is well, no, that's an orbit. The Earth is much smaller. It's only falling from here to here when I drop this, because that distance is 4,000 miles radius. So it's just a small part of a vertical orbit. If you took a body out to the to where the moon went when it first left the Earth, then you would have, and dropped it, it would drop that distance. And this is if this is a space dimension, and this is another space dimension, and that's where the circular orbit's like this, a vertical orbit is like this. Of course, it can't fall through the Earth, so a vertical orbit is just a theory. This will not drop more than a couple of feet. But I will show you what happens when, let me show you first of all the view from the other side, where you've got the X dimension here and a space dimension. So this is looking at this from the side, from here, so you see the X dimension which is coming out here. And in this case, the body is orbiting like this. It's going round, and that's going up and down here, going round and round here, and this is the R, so when you see it going up and down, you don't see any movement to the left or right because the X dimension is invisible. But all orbits are circular, and this is for a vertical orbit. And so the equation, or solutions to the equation for a vertical orbit, is that the distance is equal to the maximum distance times the cosine of the frequency times the time, and the frequency in this case is equal to 1 over the period. And this is the in radians, not in cycles. If this were cycles, omega, this is the omega, small lowercase omega, is equal to 2 pi f normally, which is 2 pi times the frequency. But I use not cycles but radians, and so we don't need the 2 pi. So this is this is the cosine representing the orbit. The velocity is equal to the maximum velocity times the sine of omega t. The acceleration would be obtained by differentiating the velocity against time. You'd get that the acceleration is equal to the maximum velocity squared divided by the maximum distance, e squared over r, as it usually is for centrifugal force. This would go back to being a cosine again of omega t. You'll probably get a minus sign in here, but the sign is usually pretty easy to work out. Now you'll notice that that's very similar to the equation for the distance as it varies with time. The distance is equal to r, the maximum distance times the cosine of omega t. So that if we now took substituted the r for this, the r here, for this r here, you would get, by substituting this r, if this r here, the acceleration would be equal to v naught squared, and instead of the r naught, we'll put an r naught here, times the cosines will cancel out, and we'll have another r over r naught. This is the one that's here, and instead of the cosine we'll put r over r naught, which means that the V squared over, or R squared over V squared is the period, so that's equal to the distance times the period. So that's squared. So that for a vertical orbit or vertical drop, the acceleration increases with the distance, which is the very opposite of what you get from Newton's law, where the acceleration, and comparing circular orbits, the acceleration falls off as the square of the distance. Here it increases with the distance. This is for a single system with a particular energy. There's more acceleration at the top than further down. This is very surprising. Thank you for watching the 9th video.